2, 1, instantaneous rate of change. And this is a controversial kind of topic, instantaneous in math, definitely. So some people might say that instantaneous doesn't actually exist at a particular point because a rate of change is what is actually changing. But there is a definition which I guess we can try to follow, or at least I can show you as a student when you're watching this, you will have an idea kind of what an instantaneous rate of change might be, okay? So when you were looking through the video on rate of change, I'll put up a link up above there, so that was kind of the initial one, you noticed that we can find the rate of change, so how the output is changing with respect to the input. And one way to do it, for example, is we have, let's say, one input, so I'll call it x1, another input x2, and what that does is if we have a particular function, it will give us a particular output, okay, so y1 and then y2. And what we did was we basically just created a slope out of those because it's going to give us two ordered pairs. So we can imagine that, so this is, okay, let's say our first, okay, so I'm going to do something like this where this is my x1, okay, right here. And then this is going to be my x2 input, and then those are, let's say, the relative outputs to those. So if I come back in here, so if I have something like that, so this would have been x1, this is x2, and let's say, this point right here, if I go in this direction, this would have been y1 and y2. And what we would do is, now we can create, so this we call a secant, okay, which is the connection on a graph between two particular points. So maybe I'll choose a different color here and try to create a secant for us. So we'll just go something like this. It's not perfect, but okay, so let's say it's that. All right, and now we can create a rate of change, which would have been the change in our y, relative to our change in our x. Now, instantaneous it actually means the same thing. The only idea is that we're trying to look at this particular rate of change almost at like a point. So here, you can have this, we have this point right here. Okay, I'm going to call that A. All right, so instead of calling it x1, x2 or something, I'll just call this A. So what we are interested in here now is around that, and ideally, okay, if we would substitute into our function, so we would get, this point right here. So what is the rate of change, okay, if we would take this particular secant and bring it closer and closer and closer to that point? So you can imagine I can take now, instead of these points, I can bring these 2 points in here, and then, I would create a new secant. And then I can keep bringing this closer and closer, okay, and then I can zoom in here. And if I keep bringing these points closer and closer, eventually, I can get as close as possible to that A. And, if I create a secant, then I can approximate the rate of change around that A, okay? So for instantaneous, depending who's defining it, so it might mean, what is the actual, so instant, which means at a particular point. Now, the controversy, as I said, comes because if you're at a point, nothing is really going to be changing there, right? So the way that you can think about that is if you have actual graphs and you're trying to find the instantaneous, okay, for now, once you get to calculus, you'll call it something different, is, what happens at that particular point. You can kind of think about that as saying that, what would be the slope, okay, that is tangent to that point at that particular line, right? But in advanced functions, when you're studying this initially, you typically, what you will do is you're still going to use this particular idea where you have 2 points, and then you're going to be bringing those points closer and closer, and then you're going to be approximating, okay, that instantaneous rate of change at that point. All right, so that's what we're going to try to do. Now, there's a few kind of definitions that you might run into Okay, so I'll bring these in here. So one of the first kind of things that I'll talk about is here preceding interval. Okay, and I'm going to just copy this. I'm going to bring it up here so that we can see it with the actual graph. And let me remove this now, right here, and talk about this idea of the preceding, okay, kind of interval. So if I remove all of this junk, all right, so it's cleaned up now. And so now this preceding interval, okay, so you'll notice that that happens for all the values of x, okay? And notice that x is actually less or equal to a. And then, okay, notice that you have a minus this h. So now the question, of course, is what is this h? Well, h is actually a very tiny number, okay? Now, you can make it big, but because we're going to be interested in instantaneous, which is what happens very close, you know, as you make that h smaller and smaller, notice what happens. This x, okay, your input gets squeezed in, okay, between the a, and it just starts approaching a closer and closer. So the preceding interval, okay, would be, if I would do this, let's say if it was further away, so this would have been a minus h, all right? So that's there, so you have this preceding interval, and that would be the distance between, you know, right here that we have. So I'm going to highlight it for us. That would have been the preceding interval. And as you make h smaller and smaller, if it's a positive number, right, so that's going to be squeezing it in and getting closer and closer to the a. So we call that the preceding interval. Now, we also have kind of the following interval. So within here, so this is what we have. So I'm going to copy this, okay, and I'm going to paste it right here. So we have the following interval, and that would be, okay, on the opposite side. So here, notice because of the plus that we have, so it's a plus h. So then what we have is this is a plus h. So you have, you know, this particular point right here. And again, you can make h smaller and smaller, you know, and you can squeeze it in closer and closer to a. Now, you can have the centered interval. So here you can have this. Let me copy this, put it back in here. Now, centered interval, notice that now x is between these two. So now we're centering it. And now this h, as it gets smaller, from both sides, it starts to approach that a, right? It's starting to squeeze it in. So this, if I would change the color, this is the following interval right here. And the entire thing, so if I would take that interval in its entirety from here to here, this would have been the centered interval. And as you squeeze that h as it gets closer, okay, it's going to get closer and closer to a. And as you make it smaller and smaller, right, as it continues on, then what happens is you can now find the rate of change, okay, and approximate as much as possible. Now, what we might typically do, okay, and you might do this in your classes with your teachers, is you might actually, you know, as you're taking the preceding interval and then the following interval separately, you might average them out because you're going to have two rates of change, okay, from the preceding interval, because it's 2 points, so you can find a rate of change, which would have been simply, okay, which would have been the secant which goes through those points. And then you can find the rate of change, which is kind of the secant which goes through those. Now, of course, as that h gets smaller, you know, these two things slowly starts to approach each other. And then when you take the average of these two, okay, 1 and 2, okay, so you would have taken the rate of change from the preceding plus the rate of change of the following. Now, averaging them out is just dividing by 2. Then you can start approximating. So that's what happens, okay? That's kind of how we approximate the instantaneous rate of change. Now, when you're doing this, and here, so there is one other item, which is this one, okay, which I kind of like to use. So now, if you want to take or an approximation or find out instantaneous interval as close as possible, this is kind of how it can be defined, and it's typically stated as and called a difference quotient. Difference means that you are basically taking, okay, so notice, so right here, it's almost like you have an input of a plus h, right? You get the output, so that would have been like your y1, okay, or y2, okay, minus your y1, which would have been right here. And then you're dividing it by the input and then the output. Now, of course, because you're going to have, so notice what happens, a plus h minus a, well, then the a minus a will cancel and you only have an h at the bottom. That is called a difference quotient in between. And as you make the h smaller and smaller and smaller, then you start to approximate the instantaneous rate of change. I'm going to show you how to do that on an example. All right. Now, it's interesting because we typically say, okay, so h is going to be some, very small number, but it is typically both positive and negative. So, it could be this. You might want to make it smaller. Maybe it's going to be something like this. Okay, or maybe it's going to be something like this. Okay, and then you can continue on, of course, and make it as small as possible. So the smaller that you make it, okay, then the better approximation that you have. Now, typically we round our answers anyway, so you don't necessarily have to go super small. But, if you go to 0.001 or something like that, it would give you a good sense of what that instantaneous rate of change is through this calculation. Now, because I put in here, so you can see I put in here both positive and negative. So if we would substitute that into this difference quotient, we would kind of have to do two different calculations. One for the positive, which really is like the following interval, right? And then one for the negative, which is like for the negative or the preceding interval. And if you're going to combine both of those, that's like utilizing the centered interval approach, right? Finding the two. Once we find the two, we can get the average, and then we can approximate what that rate of change might be. Okay, so that's where we are at the moment. Okay, so let's take a look, okay, and see what happens. So here is an example of a function. Now, let's graph this so that we can kind of see, and I'm going to try to bring it into our notes. All right, so here's decimals. I'm going to graph this function. So it's 2, I guess, to the x minus 1. Okay, and now it says that we want this, our a, okay, so the point where we're trying to approximate. You can pick any point, it doesn't matter. So they said 1, so I'm going to put that in here. All right, so that's that. And sure, we can label it so we have it like that. Okay, so that would have been our answer. Now, okay, so what we're going to do is, okay, we're going to try to take this up. I'm going to take a screenshot of this, okay, and then we're going to work on it. All right, so here, that's what we're going to have. I'm going to put it done. Let's load it in here, and let's try to find the instantaneous rate of change, okay, and see how we could possibly do it. So I'm going to add our, again, we just added this in here. So we have that, okay. And now what's our goal, right? What do we want to be able to do? If I'm going to be using this, okay, which is going to be our difference quotient. So this right here. Okay, and we're going to try to calculate. So for us, okay, so this is our function, all right? Our a, so the point we're trying to find the rate of change at, is this, okay? And if I use this difference quotient, then what it's going to be is, okay, it's going to look like kind of like this. So this is my, my a right here. And then what I'm going to do is I'm going to, let's say, on both sides. Okay, so something like that. Okay, so we have, just want to show you visually what is happening. So what we're doing is, okay, so we have, this would have been, okay, so this is my a right here, okay. This is going to be a plus the h when, let's say, h is positive, okay? And this is going to be a minus the h. So here we're going to assume that h, is plus or minus some very small number, all right? And what we're going to be doing with that, we're going to be trying to squeeze it in and try to approximate, okay, what that change might be. So let's take a look. So now we want to be able to find it out. So let's say h, okay, was equal to, let's say, plus minus 0.1. Okay, so it's going to be our first try. So what happens in that case? Well, in this case, what happens is that a plus h, okay, is equal to, so now let's take the positive amount. So that would have been 1 plus 0.1, which is 1.1. So a is going to be 1. And then a, if it was negative, this would have been 0.9 because we just took away 0.1. So we can find, so from here, we're going to be able to find our difference quotient. And then also, so from the following interval and from the preceding interval. Okay, so we're going to have kind of two calculations. So here is my first calculation. So that's the following interval. And then I'll do the preceding interval. So let me do that in kind of fast forward fashion. That's all I'm doing is just substituting the numbers in and then finding, okay, my difference quotient. So that's what I'm going to do. Okay, so I'll be back. All right, so before I do the calculations, okay, so what I wanted to do is I wanted to just kind of graph this on decimals. So notice I put the function in, I put a is equal to 1, I put h is equal to 0.1, and then it kind of gets, it's between 0 and 1, so we can make it as small as we like. And then I plotted the actual points. So the one at a, the one at a plus h, and a minus h. And what I wanted to show you is, you get this squeezing effect. So as you get closer and closer, okay, so happens. So if I now, because I'm sliding this, notice as I slide this, okay, so I'm going to kind of do this so you can see it. Notice that it gets closer and closer and closer and closer and closer and so on, okay, to that A. And that's why, we are going to be able to approximate that rate of change, okay, if we would draw an actual secant. It would approximate at that particular point, kind of the tangent, okay, or the slope that goes through that point pretty closely, all right? So that's ultimately what our goal would be, okay? So now what I'm going to do is I'm going to actually calculate, okay, so that we can kind of see what that actual rate of change might be, okay? So give me a moment. All right, so what I did was I just inputted the numbers in and then calculated, okay, so our rate of change, okay, for the h, which is 0.1, and both on the positive side and then the negative side as well. And we got two of these. So now what we do is, because we have two of them, we take the average over the two. So taking the average of these, these are approximately, so 1.435 plus 1.339 equals, and then we get our answer divided by 2. So we have an approximation of, okay, 1.387 as kind of our instantaneous rate of change. Now, I don't know, here we don't have any units for this function, but that's what kind of the slope might look like, okay? So it's kind of the slope 1.387. So the idea here is, okay, if you want to really get a good approximation, instead of using h, which is 0.1, you can use, like h, which is, 0.0001, for instance. So let me, pick that. So if I would pick h is equal to 0.0, let's say 0.1, okay, what would happen in that case? And we're going to get closer and closer to our actual kind of slope, when the instantaneous change at A is equal to 1. So let me do this calculation now as well, okay, and then I'll be right back. All right, okay, so I put this in. I mean, it takes a little bit of time as you start plugging in. I also, on the top left, you can see how it really squeezed around that 1. Now I also used the calculator to actually try to see. So I set H was equal to 0.001. And this is kind of how I set it up in decimals. Notice that's the nice thing if you're kind of trying to learn decimals, to set these things up. And now I plugged this in, and notice that, look how close they are now, right? So this is plus on the plus side, and this is on the minus side. So the preceding and then the following. This was the following interval, preceding interval, so we're kind of centered around the 1. And now look how close they are. So if I take the average, if I'm going to add these two up, okay, now I can find out. I mean, you can use as many decimals as you like, and just kind of keep them in here. So we have 1.385814, and then we have our answer divided by 2. So my average, okay, and my instantaneous, so it's approximately, give or take, so something around there. So 1.3, let's say 6. Okay, we'll just keep. And notice our original. So here was when we used 0.1 and we took the average, we got 1.387. And notice this is 1.386. So they were very close already. Now, not for all functions. You'll see that just because you used 0.1 and then you used something smaller, they're kind of the same. So sometimes students think, well, then I guess I don't have to really use that small of an h. It will honestly just depend on your function and, how kind of crazy it's acting at or around a particular point. Now, most of them, they're kind of smooth, so it's pretty simple, especially the ones that you use in advanced functions course. But I hope, by doing this and also plotting it out, like plotting it like this, okay, might give you a sense of, how you can approach these. And it's beautiful to see when you are doing and dealing, okay, with this, and you can just kind of slide these things in and out, okay, as you're going through these. So it's pretty cool that you can go, as close as you like or as far as you like, whatever that might be, okay? All right, so thanks for watching. So that's kind of a introduction to instantaneous rates of change. Bye, everybody.